Hi everyone, welcome to another video for research design and analysis. This is our third video in the series on one-way analysis of variance, which is when we have one categorical factor that has multiple levels. So in today's video, we're really going to focus on building our regression model where we code those different levels of our categorical factor using either contrast codes or treatment codes, similar to what we did in previous videos with the independent samples t-test. So for this example, we're going to focus on these data where a researcher was interested in how children respond to feedback, and then this leads them to take different numbers of attempts on different tasks. So children were kind of exploring these different tasks, and they were either given negative reinforcement, or essentially they were given failure feedback, right, when they made errors, and then we look at the number of different tasks that they tried. They were given no feedback, where we don't really tell them, are they doing a good job, or are they doing a bad job, and then we look at how many tasks they tried. And then we give them positive reinforcement, where we focus only on their successes and reinforce their successes, and then we look at the number of different tasks that they attempted. So we can look at those data in either a tabular format here, we can summarize them with histograms, right, where we look at the number of attempts taken for children who receive failure feedback, the number of attempts taken for children who received no feedback, and the number of attempts taken for children who received success feedback. We can then plot these data kind of with individual data points and box plots over here on the far right-hand figure, where one of the things that I think jumps out then really is we get this increase in the number of attempts taken as we move from negative reinforcement to sort of the neutral control condition to positive reinforcement. So this is, an interesting situation because, again, now we have categorical differences between our groups. We don't have continuous predictor variables, right? We have, you got negative reinforcement, you got no reinforcement, or you got positive reinforcement. So how do we categorically represent these categorical differences numerically? So this is a very similar situation to what we were doing when we were looking at the independent samples t-test, and we said, we have a treatment group and a control group. So how do we code those two groups in order to actually use them in a regression model? And the answer here is the same. We're going to use either contrast codes or the treatment/dummy codes that we used before, but now we have an additional number of groups. And the way that we code these variables will then affect exactly what the individual slopes and intercepts mean in our different models. And there are strengths and weaknesses to both of these approaches. In general, we're going to like contrast codes, even though they make interpreting the individual slopes a little bit harder. And we will probably avoid treatment codes because even though they help with the interpretation of individual effects, they make it a little bit harder to interpret some of the effects of multiple variables in our model, and therefore, we're not going to like them as much when our models get bigger and more complicated. So first, though, let's focus on our contrast codes. And remember that for contrast codes, we need the levels of our code to sum to 0. But now we're going to have an additional wrinkle because now we have more than two groups. So we're going to need more than one contrast code. And as a rule, you always need a number of codes, one less than the number of levels of your variable. So in the past, when we had just a treatment group and a control group, we could get away with one code because we only needed to say, were you in the treatment or the control? Now, though, we have the failure group, the no feedback group, and the success group. So we have 3 levels to our categorical variable, which means we're going to need 2 codes to represent all of the different levels of that variable. And when we add in multiple codes, we have an additional consideration when we're generating these orthogonal contrasts. So for our first code, right, what we can do is we'll code failure as -1, feedback as 0, and success as +1. So this is a linear contrast because what it's looking at is going from kind of failure to success. We're coding failure as one end of the spectrum and success as the other end of the spectrum. And in this experiment, that makes a lot of sense because that is kind of how positive and negative reinforcement line up with each other. If we have kind of a low to a neutral to a high dose of something or exposure in our treatment, we'd probably want to code them in this way so that then our first contrast is going to tell us about this condition relative to this condition up here. Our second contrast code, we're going to now have 1, -2, and 1. And this is a little bit more complicated as a code, but because you can see success and failure are both coded as 1, then this contrast is telling us about the middle condition relative to the average of the two extreme conditions. So this is a quadratic contrast. Rather than saying, okay, are we linearly moving up as we go from one point to the next, we're essentially asking, should this bend in the middle at all? Is the no feedback condition different from the average of these two conditions? And again, for this design, this code makes a lot of sense because we were going from kind of a low end to a neutral ground to a high end. So it's very reasonable to say, is this different than what we would expect if we just averaged the low and the high together? And if it is, that's interesting because that suggests that there's something, beyond just kind of being in a moderate range here. There's actually some nonlinear effect to this manipulation. Now, we have these two codes, right? And we can see that if we add across, they sum to 0. -1 plus 0 plus 1 is 0. 1 plus -2 plus 1 is 0. But now that we have these two codes, we have to make sure that they function together as a set. So we're also going to check their cross product. So we're going to take -1 times 1, that gives us -1. We're going to take 0 times -2, that gives us 0. And we're going to take 1 times 1, that gives us 1. And these cross products also sum to 0, which means we now have an orthogonal set of contrast codes. So they're completely independent of each other. And that's going to be important because it's going to help us interpret some of these effects if we know that our codes are independent. So for these contrast coded factors, right, let's assume that these are the codes that I used and I created two new variables to look at. I'll call it con.c1 and con.c2. Right, so this is a contrast-coded variable that tells me everyone in the failure group got a -1, everyone in the no feedback group got a 0, everyone in the success group got a +1. Con.c2, everyone in the failure group got a 1, everyone in the no feedback group got a -2, everyone in the success group got a +1. Right, and then we'll put these two variables into our regression model. So we're predicting the number of attempts as a function of both con.c1 and con.c2. And when we do that, we have two variables in our regression model. So we can first look at the test of the overall model. And in our next video, we're really going to go into detail about this f-test. But for now, just look at the fact that we have 2 degrees of freedom here, indicating that we are testing these two codes simultaneously to see if, as a set, are they reducing a significant amount of variance in our dependent variable. And what we find is that the p is 0.052. So if we had set our alpha level at 0.05, this would not be statistically significant. And we wouldn't actually have a statistically significant reduction in the error here based on the p-value. Now, the other thing that we have to look at, though, is the actual values of the intercept and the two different slopes that make up this regression model. So we get those out of, this is an example from a Jamovi output, but you'd get something similar from R or SPSS. And we're looking at the estimate of the intercept, the estimate of the slope for con.c1, and the estimate of the slope for con.c2. Now this intercept is 3.708. And this is interesting because remember the intercept is always the predicted value of y when x is 0. So when is x 0 in our contrast-coded scenario? Well, x is 0 on average across all levels, which you can see a little more clearly if you actually add up all of these different levels, right, and then divide by the number of observations that there are. So -1 plus 0 plus 1, right, is 0. Plus 1, we're at +1, -2, we'd be at -1, plus 1, we'd be back to 0. So the total of these 6 numbers is 0 divided by 6, right, gives us 0. So 0 is on average across the groups. So this intercept is actually the mean of the group means. And that's really useful because this is then saying, okay, on average across groups, the number of attempts was 3.7083. And this is one of the really appealing things about contrast codes, is that they simplify the interpretation of different variables in our model. So in this case, we're just looking at it as the intercept. And this is the intercept then tells us, on average across groups, what was the number of attempts. But you can think about it as if we're adding other variables in, like let's say we added, gender as a variable or age as a variable. We might want to know what was the effect of age on average across conditions. So in order to be able to ask about the effect of one variable on average across the conditions, we're going to have to contrast code these factors. Now, the trade-off in that is that then these individual interpretations of the slopes are a little bit trickier with contrast codes. So they make the interpretation of other variables easier, but they make our interpretation of the intercepts a little bit more difficult. Because, for instance, for con.c1, we get a slope of 0.6875. And remember that the slope is the predicted change in y for a 1 unit change in x. Well, on con.c1, changing by 1 unit takes us from failure to the no feedback group, and changing by another unit takes us from the no feedback group to the success group. So it's actually a 2 unit change that we have to do to get from failure to success, right? So this 0.687 is what we get for a 1 unit change, so we'd have to double it. But this slope then is half of the distance between the failure and the success group, right? So the success group on average did about 1.4 more attempts than the failure group, because it's 0.687 times 2, right, in order to get the actual difference between those two conditions. Now, you could maybe change your code here to make this a little more interpretable. So if we had used like negative 0.5 and positive 0.5, then a 1 unit change would be directly between those two conditions. So the way that you code these variables can help make these estimates more interpretable, but in general, the interpretations get a little bit trickier when we're looking at these things as contrast codes. But like I said, there are some really strong reasons to prefer contrast codes because they'll simplify our interpretation when we're looking at other variables. Now, the alternative version of doing this is to look at treatment codes or dummy codes, and they have essentially the reverse property of the contrast codes. They make it a little bit easier to understand the difference between two conditions that are being directly compared, but they really can make it hard when you have other variables being added into your model, because then you have to keep very careful track of exactly how each thing is coded, and it can be very misleading what slope you're looking at and how you're supposed to interpret it. So we'll get to that more as we add variables to these models, but for now, let's just look at how we would dummy code our 3 levels here. Again, because we have 3 levels, we're going to need 2 codes in order to represent all of the different groups that we have. So we're going to need 2 dummy coded variables here. So in the first case, we're going to call failure a 1, no feedback a 0, and success a 0. In the second case, we're going to give failure a 0, no feedback a 0, and success a 1. And the reason that we're going to do this is because your reference group is going to be the group that's coded as 0 across all levels of the code. So here, the no feedback group is essentially like our control condition. And previously, right, we made the control condition 0 and the treatment condition 1 when we only had 2 levels. Here we have 3 levels, but it's going to be useful to always compare back to the no feedback condition. So by making the no feedback condition 0 in both codes, code 1 then is going to compare back to the reference group, and code 2 is going to compare back to the reference group. So essentially, we'll be comparing failure to no feedback and success to no feedback. And this is then going to make informative slopes that will tell us about the difference between the failure condition and the no feedback condition, and the difference between the success condition and the no feedback condition. So if I have these treatment coded factors entered into my model now, one of the first things to notice is that the actual R, R squared, and F test all stay exactly the same. And the reason for that is that these two models are going to be making the same predictions. So they're going to reduce the sum of squared errors to the same degree. As long as we've done either of these two sets of codes properly, we'll get the exact same model fit. Right, so we're not going to have any issues in interpreting this omnibus test or any of the analysis of variance tests that we'll do based on our coding. Where it does make a difference, though, is in these estimates. Right, so we can start with the intercept, and we can see that it's a little bit different. Now it's 3.75. And again, right, the definition of the intercept is always the predicted value of y when x is 0. When we had contrast coded our factors, the predicted value of y when x is 0 means on average across our different groups. But here, for x to be 0 across both codes, right, you have to be in the no feedback condition. Because in our first variable, right, con t1, 0 could mean you're in the no feedback group or the success group. But for con t2, 0 means that you're in the failure group or the no feedback group. So in order to be 0 on both x's, right, you have to be in the no feedback group. So now, rather than being the predicted value on average across groups, 3.75 is the mean number of attempts in the no feedback group. Now, the nice thing though with these treatment codes is that the subsequent slopes are a little bit easier to compare because we're just making a comparison between each of the positively coded groups back to the no feedback group. So this is looking at failure relative to no feedback. They did 0.75 fewer attempts because again, the slope is the change in y for a 1-point change in x. So if we go from no feedback to failure, that's a 1-point change. And the failure group did 0.75 fewer attempts. Similarly, for the second treatment code, right? This is the change in y for a 1-point change in x, and that 1-point change is going from the no feedback group into the success group. So that means then that the success group did 0.625 more attempts than the no feedback group. So these two estimates are a little more straightforward in terms of they represent the difference between the failure condition and the no feedback condition for T1 and the success condition and the no feedback condition for T2. And we can see that although one is negative and one is positive, neither of those differences is actually statistically significant in our model. So let's unpack this a little bit more, right, and look at what we're going to get out of this when we analyze this in a statistical program. Because you can do treatment coding and you can do contrast coding, but the main lesson is you need to be mindful of what code you use and then how it's going to affect your data. And one of the things that we first saw is that regardless of which code that we use, we get the same overall model test. So the omnibus F test, which tells us about the variance explained by our predictors as a set, was not statistically significant, but it was the same regardless of what code we used. It was always 3.41 with 2 and 21 degrees of freedom that led to a p-value of 0.052. And in the subsequent video, we're going to get into more detail about this F-test and how it's calculated. But the main thing right now is just to recognize that regardless of what coding scheme you use, you get the same model fit. And again, the reason for that is that your model is making identical predictions. It's going to predict the mean of the failure group for everyone in the failure group. It's going to predict the mean of the no feedback group for everyone in the no feedback group. And it's going to predict the mean of the success group for everyone in the success group. So the model fit statistics will all be exactly the same, regardless of how we coded it. Now, one of the things that we also then have to look at is what goes into this calculation of the F-test. And again, we're going to get into more detail about this in the next video. But note that the F-test is a ratio of the mean squared error explained by the regression relative to the remaining error in the residuals. So in previous videos, we've talked about calculating the sum of squared errors explained by the regression, right? And then getting the sum of squared errors left over, what's in the residuals, and how those two things are going to add up to the sum of squared errors total. What the F-test allows us to do then is look at this reduction in the sum of squared errors and say, did we explain a statistically significant amount of the variance given the number of predictors that we used? So we're going to take the sum of squared errors divided by the degrees of freedom to get the mean squared error, and that will tell us then on average how much variance did each of our predictors explain. And then we'll take the ratio of the mean squared error of the regression to the mean squared error of the residuals, so 3.79 divided by 1.11 to get 3.41. So in this case, we explained about 3.41 times the unexplained variance with our model. And that's pretty good, but given our limited sample size, that's not statistically significant in this situation. But again, right, this is just based on the model fit and the reduction in the sum of squared errors, which provided that we've coded either using appropriate treatment codes or appropriate contrast codes, isn't going to depend on the way that we've coded our variables. We're still going to get the same variance explained and then ultimately the same F and P value for the omnibus test of the model. Now, where do we get these degrees of freedom? Well, the degrees of freedom, right, as you might recall previously, depend on the number of parameters that we're estimating. So for the effect of condition, right, in this case, we need to estimate 2 parameters because we need 2 contrast-coded variables, right, to represent all 3 of our conditions. We always need 1 less code than the number of levels that we have. So in this case, we had 3 levels. which means we need two contrast-coded variables, x1 and x2, which means we need to ultimately estimate two parameters, beta1 and beta2. So we're estimating two parameters here to get the first degree of freedom for our f-test. Now, the second degrees of freedom, those for the denominator, are based on the number of observations minus the total number of estimated parameters in our equation. So remember that in our equation now, we also have an intercept. So we have 24 total data points in this example, and we actually have 3 total parameters that are being estimated. We have the 2 that are being estimated for the effective condition, but we also have 1 for the intercept. So 24 minus 3 is 21. So we have 2 and 21 degrees of freedom. So we have 2 and 21 degrees of freedom for this f-test. And finally, right, where our choice of contrast codes actually makes a difference is down here in the interpretation of these intercepts. And we'll get into more detail about contrast codes versus treatment codes in these situations, but I think the main thing to be aware of is that different statistical programs choose your contrasts for you, and you need to be aware of what contrast it is making in order to interpret your slopes and intercepts correctly. Again, regardless of the contrast, the f-tests and the ANOVA table, all of that stuff will work out the same because it's based on the reduction in the sum of squared errors. But down below, the individual estimates of these parameters are affected by how you code your variables, right? Because what x equals 0 means makes a big difference. So in this case, this is an example output from Jamovi. Jamovi uses treatment coding by default, and it makes the first alphabetical level the reference level. So rather than making the no feedback condition the reference, it has chosen to make the failure condition the reference because it is the first level alphabetically, right? F comes before N and S. So this intercept then is the predicted value of y when x is 0. X is 0 on both of our variables when someone is in the failure condition. So the failure condition had an estimated number of attempts of 3. The no feedback condition then is getting captured relative to the failure condition by the second code. So the no feedback condition did, on average, 0.75 more attempts. So they had a mean of 3.75 attempts, right? And the success condition relative to the failure condition did, on average, 1.375 more attempts than the failure condition. So the success condition, on average, did 4.375 attempts. And you can see that, again, the no feedback condition relative to the failure condition, that is not a statistically significant difference. But for the success condition relative to the failure condition, that is a statistically significant difference, right, of 0.016. However, we really don't want to delve into the interpretation of these individual coefficients too much because as a set, we didn't actually have a statistically significant reduction in the variance here. Now, how much we are kind of justified in doing that is a complicated question because, looking at these things might be justified, for instance, in the case of a strong a priori hypothesis, where if we don't assume that we're just kind of randomly testing an equivalent set of conditions, we might not be worried about what we get for the test of the omnibus test here. And we might really be justified in focusing on some specific planned contrasts down below in our data. All else being equal, though, we're going to want to look at this omnibus effect first, because if we don't get a statistically significant reduction in the variance up here, running additional tests by looking at the individual parameters down here is ultimately just going to contribute to our false positive rate. So exactly how you interpret that and kind of how you think about what tests you need to do very much depends on the theoretical motivation, the amount of previous work in the area, what your intention is. I'm not saying we should base that decision just on this p-value alone, but if, for instance, these were kind of random conditions and we didn't have a strong reason for thinking that one difference should be bigger than the other, then our false positive rate is a concern, and we might not want to proceed with any post hoc tests if this omnibus F test is not statistically significant.